So there are three classical states of matter, and you've heard of these before. We have solids, liquids, and gases, and you can see I'm sort of writing them in an order here, and that's because they increase in energy. That's our first sort of big idea behind these states of matter. Solids are the lowest energy, then we have liquids, and then gases at the next level. Energy is just one of the characteristics that we can examine of solids, liquids, and gases. We know that they increase. We can also look at volume. Volume is another physical property. So let's look at the volume that's characteristic of solids, liquids, and gases. Solids always have a definite volume. Okay, it doesn't change. If you have a solid object, its volume is fixed. Okay, it's not going to change unless you do something to it. Liquids are the same way. Liquids have a definite volume. Gases have an infinite volume. Okay, gases have an infinite volume. A gas will try to take up as much space as it possibly can. It'll only be contained or restricted by whatever container it's in. Another property we can look at is shape. Okay? Solids have a fixed shape. If you have a stapler, that's a solid. Okay? The stapler is not going to change its shape on its own. It's fixed. Liquids are a little bit different. Liquids take the shape of whatever container that they're in. So if you pour liquid into a cup, you now have liquid in the shape of a cup. If you pour liquid onto the floor, you now have liquid in the shape of a puddle. Gases are kind of similar to liquids in that they also take the shape of the container. Now there's a small difference here. Liquids will try to fill whatever container they're in. So their shape really depends on how much they can fill that container. Whereas gases automatically take the shape of whatever container they're in because they have an infinite volume. They can take up as much space as possible. The next thing we want to look at is particles. Okay? We're going to look at particles of solids, liquids, and gases. So I'm going to have three boxes here. I'm going to fill them in. And you should draw these boxes as well. Let's pick a substance here. Let's use carbon dioxide. So I'm going to put carbon dioxide in each of these boxes, and we're going to use different states in each box. So in terms of notation, in the first box, I'm going to have CO2, carbon dioxide, little parentheses surrounding this S here. And that notation means that this is solid carbon dioxide or dry ice. Okay. The next one we have liquid carbon dioxide. So I have a little cursive L there in parentheses to indicate that this carbon dioxide is a liquid. And I have, my last box is going to have a gas, so simple G for gas. I'm going to have a little key here making particle diagrams. Okay, we should get some practice in class. But for this diagram I have a little red dot. That's my particle. That's going to represent carbon dioxide. So let's look at the first box. We have carbon dioxide in a solid form. So I have my arrangement of solid carbon dioxide particles. You'll notice they're in a very regular geometric pattern. I have them in a grid because solids form a very regular geometric pattern. They're also going to be fixed in position and not really moving around. They kind of vibrate in place a little bit, but their position is fixed. Okay, they're going to stay in this rigid, fixed position. It's a sort of geometric arrangement. If I go to the liquid, they're going to be close to each other. You're going to see they're going to be close to each other, like the solid. But these particles, a little bit more spread out. Okay, a little bit more spread out. They're not all over the place. They're still near each other, but they're more spread out. And in the gas, now we have carbon dioxide gas particles. These guys are going to be all over the place. Okay. Really spread out here. They're very far apart from each other. They're totally random in this space where you're going to find the particles of a gas. So let's write that down. We have arrangement of particles here. Arrangement's important. So for the solid, we have a fixed arrangement. Okay. a pattern. In a liquid, they're random but close to each other. And in the gas, they're random and moving, sort of zipping around all over the place here. They're moving and they're far apart. They try and stay far apart from each other. Okay, so that's the arrangement of particles in these different states. There's one last thing we want to look at for particles of a solid, liquid, and a gas. And the last thing we want to look at is the attraction between the particles. So the reason that they're in these arrangements, okay, in this tight pattern over here and in this completely random one over here, has to do with the attraction between these particles. And that's something we're going to get into a lot more detail with later, but let's get the general trends down right now. So in the solid, there are strong attraction. There's strong attraction between the particles. In the liquid, there's enough of an attraction to keep the particles close. To keep particles close. And in the gas, very weak attraction, basically negligible. Okay? So insignificant, they really don't affect anything. Negligible. So that concludes our look at matter and properties. If you have any questions, make sure you write them down as part of your notes and bring them into class with you. A very quick look at some non-classical states of matter. So these are two examples. There are more, but plasma and the Bose-Einstein condensate are pretty interesting. So we're going to take a quick look at what these things are. Plasma is sometimes called the fourth state of matter. Okay, so we have the first three, solids, liquids, and gases, in increasing energy, and plasma is sometimes considered the fourth. It's basically what happens when you superheat a gas. Okay, so it's even more energy than a gas. And when you do that, something really interesting happens. The electrons separate from the atoms, and you get a whole bunch of unique properties that's associated with that. Now what's really interesting about plasma is it's actually the most common state of matter in the universe. Even though it's hardly ever, you would hardly ever see it on Earth. In fact, one of the few times we see it naturally is when you see lightning. Okay, you're seeing air become a plasma temporarily. That's that bright flash that you see. But this is actually the most common in the universe because stars are made of plasma. The other example we're going to use here, and there's of course other non-classical examples, but the other example we're going to look at is something called the Bose-Einstein condensate. So for plasma, we saw what happens when you heat up a gas really far. For a Bose-Einstein condensate, this is what happens when you take a substance and you cool it down to incredibly low temperatures. Okay, very low temperatures. In fact, you have to get close to absolute zero before this is even possible. Close to absolute zero. Okay? And something, just like plasma, something very interesting happens here in that at this very low, close to absolute zero temperature, atoms basically clump together. Okay? And they stop being individuals. And you get this sort of super atom blob that is made up of all the atoms that just clump together, and it acts as one thing. That's a Bose-Einstein condensate, and it's another state of matter that's sort of non-classical is what we call it.